Professor Clements with you as we again consider electric circuits, this time with battery and resistors. And our challenge here would be to find the power in each resistor. How would we calculate power? The basic concept, power equals current times the potential difference across the device. So we're going to need to find the current in each resistor. To do so, we need to simplify the circuit down to just one resistor and the battery, find the current coming out of the battery, and then work our way backwards step by step so we can find the current in each branch of the circuit. To start this process of finding the single resistance, we must first do the parallel combination of the 6 and 13 ohm resistors. The 1 ohm is not in a simple series connection with either the 6 or the 13, so we do this parallel calculation. As you see, I found 4.105 ohms. This is plausible because when we do this reciprocal calculation, we know that the value we obtain should be less than the smallest resistance in the parallel combination. So we have that. We can make a new sketch of our circuit with a 1 ohm and a 4.105 in series. That's an easy addition calculation, and we find 5.105 ohms is the net resistance of that first circuit. So we have achieved a first simplification, first step. We're ready to find the current from the battery, and V equals IR. Rearrange I equals V divided by R. We find 2.351 amps coming out of the battery. This is also the current in the 1 ohm resistor. It is not the current in the 6 ohm resistor nor the 13 ohm resistor. Those two resistances are going to have a split of the 2.351 amps. So what is the voltage across the parallel combination? Well, we can use V equals IR to determine that. We know the current in the 4.105 ohm resistor is the same as the current in the battery. So we can take 2.351 amps times 4.105 ohms. We find 9.649 volts across the parallel arrangement. With that, again, we can use V equals IR and find the current in each branch of the parallel resistance. 9.649 volts is the voltage across both the 6 ohm and the 13 ohm resistor. They're in parallel, their voltage is the same. So we calculate the currents, just doing V divided by R, and we add them up and we get a little opportunity to check our work. The sum of the currents in the two branches, 2.35 amps, is the current, the total current coming out of the battery, the total current going through the 4.105 ohm parallel net resistance. So that checks out. Now power in each resistance. The potential across the 1 ohm resistor can be calculated with I times R. The current coming out of the battery, 2.351 amps times the 1 ohm, 2.351 volts. So that power, I times V, would be 5.52 watts. The current in the 6 ohm is 1.608 amps and 9.649 volts there, so 15.5 watts. The power in the 13 ohm resistor, its current is 0.742 amps, 9.649 volts across it, so 7 watts. The sum is 28.2 watts. And now if we do this power calculation for the battery, the current coming out of the battery, 2.351 amps, 12 volt battery, 28.2 watts. The power coming out of the battery matches the power being delivered to the resistors. So we've double checked ourselves. We've simplified the circuit down to a single resistor, calculated the current coming out of the battery, and then worked our way back to find the voltage across each element of the parallel combination and find the currents going through those. Then P equals I times V gives us the power. Keep practicing.